Today, let us look at hydrates of non-metals. There are very interesting questions on this particular topic. And look at these hydrates of fourth group: CH4, SiH4, GeH4, SnH4 and PbH4. Methane, silane, germane, stannane, plumbane. What is the sound common? Ne. Ne. So, better hydrates be called Ne. Methane, silane, germane, stannane, plumbane. That's why we call BH3 as borane and B2H6 as diborane. You must have heard about that, diborane. So, the sound Ne suggests that it is a hydride, especially non-metal hydride, diborane. It is also a hydrate. Now, these are the hydrates of group 4A: carbon, silicon, germanium, stannum, plumbum. And hydrates of fifth group: NH3, PH3, phosphine, ASH3, arsine or arsane, phosphine, arsine, stibine, bismuthine. And the hydrates of sixth group: H2O, it is water. No point in calling it oxane. Of course, it may be called oxane, but there is no point in calling it oxane because it is popularly known as water. Everybody knows water. H2O, H2S, H2Se, H2Te, H2PO. So, carbon, silicon, germanium, stannum, lead, nitrogen, phosphorus, arsenic, antimony, bismuth, oxygen, sulfur, selenium, tellurium, polonium. We have covered three groups. And the halogens, when they combine with hydrogen, they better not be called hydrates. They are hydrogen halides. Hydrogen halides. Hydrogen halides. HF, HCl, HBr, HI. Hydrogen iodide. So, they are not, strictly speaking, they are not hydrates. In a hydride, HF, HCl, HBr, HI. Hydrogen fluoride, hydrogen chloride, hydrogen. This is hydrogen sulfide, hydrogen selenide, hydrogen telluride, hydrogen polonide. So, what are the questions? What are the questions that are possible? First, let us discuss a few concepts and then we can go to questions later on, not now. Now, first question on hydrates is their stability. Stability of hydrates of non-metals. Stability of hydrates of non-metals. Small atoms form stronger bonds. Small atoms form stronger bonds. Everything about halogens is an exception. Everything about halogens. I am not talking about compounds of halogens, mind you. I am not talking about compounds of halogens. I am talking about halogens in their elementary state. Everything about halogens is an exception. Slightly unexpected things happen in halogens. So, small atoms form stronger bonds. So, when I say HF is stable, HF is thermally stable. What do I mean by that? HF is thermally stable. When I say that, HF on heating doesn't give hydrogen and fluorine atoms easily. That is what is meant by thermal stability. You heat HF to a temperature of 400, 500, 600. Even at a very high temperature, it doesn't break into hydrogen and fluorine atoms easily. Why? Why does it break? Because the HF bond is very, very, very strong. It is a highly polar bond. It is very, very strong. So, small atoms form stronger bonds, and a molecule formed by smaller atoms on heating doesn't decompose easily Therefore, it is said to be thermally stable. So, the thermal stability of hydrates of fourth group, methane, silane, germane. Now, predict which is most stable? Methane. Why? Carbon is a small atom, carbon hydrogen bond, silicon hydrogen bond is a little longer. So, smaller the size, greater will be the overlap and stronger will be the bond and more stable is the molecule. Smaller the size, greater the overlap and stronger will be the bond. So, carbon hydrogen, silicon hydrogen. So, methane, stability, methane is more stable, not less stable. Stability of methane is greater than silane, greater than germane, like that. Greater. Methane, silane, germane, stannane, plumbane. Now, so plumbane on heating easily gives lead and hydrogen. You can easily get hydrogen from plumbane. And what about the other? NH3, PH3. NH3 more stable than PH3, more stable than ASH3, etc. H2O more stable than H2O, more stable than H2S, more stable than H2SE. HF more stable than HCl, more stable than HBr, more stable than HI. That's all. Okay? Why? Smaller size, small size. But what about halogens? That is a different ball game altogether. F2, FF bond is very small, but there are too many lone pairs. Because of too many lone pairs in too little space, fluorine is a small atom. So, the bond strength does not depend on attractions alone. Repulsions also matter, repulsions. So, the bond energy expected order is F2 greater than Cl2. The expected order of bond energy F2, FF bond greater than Cl bond greater than Br bond greater than II bond. Don't be mistaken, this is the expected order. And will you get the expected order? No. Everything about halogens is an exception, I told you. So, instead of fluorine being the strongest bond, FF being the strongest bond, fluorine, which should have been the winner, ends up in the third place. The bond energy of Cl greater than Br, fluorine bond is even weaker than bromine bond, though fluorine is very small, and that is the reason, smallness itself is the reason why too many lone pairs in too little volume. Of course, you have lone pairs in chlorine also, 3 lone pairs, but they are a little away, so lesser repulsions. So, this is everything about halogens is an exception, because in general small atoms form stronger bonds, but here it doesn't happen like that. Now, second, reducing ability of hydrates of non-metals. Reducing ability. HI is a good reducing agent. In fact, the most powerful reducing agent as far as organic reactions are concerned, red phosphorus plus HI at 250 degrees centigrade, all oxygens are converted to H2O. All oxygens go out from a molecule. Even a molecule like glucose C6H12O6, when you heat that with red phosphorus and HI, what happens is all oxygens will go away and you get C6H14 hexane. You get hexane, N-hexane, normal hexane. So, even 6 oxygens have been removed by HI. What will happen to them? Of course, they become 6H2O. Means enough hydrogens are supplied by HI on heating. So, and 2 more hydrogens are given for C6H2 as well. So, HI is a good reducing agent. Why? The reason is reducing ability means the ability to give hydrogen atoms on heating. On heating. Who do you consider a good reducing agent? Who do you consider a good reducing agent? A compound which on heating gives hydrogen atoms easily must be considered as a good reducing agent. And what is the logic? Small atoms form stronger bonds. small atoms form stronger bonds. So, reducing ability of hydrates of nonmetals, is inversely proportional to their stability. Reducing ability of hydrates of nonmetals is inverse to their stability. If a molecule is very stable, how can it give hydrogens on heating? It doesn't. Therefore, reducing ability order, let us write for a few. Methane less than silane less than germane, it is the inverse order. Okay? Because the germanium hydrogen bond is taller, it breaks easily. Same is the case with HF bond. HF bond is very HF, HCl, HBr, HI. That is why HI happens to be a very powerful reducing agent. So, even in fourth group, every group, fifth group, H2O, H2S, which is a better reducing agent? H2S. Why? Sulfur hydrogen bond is weak. Oxygen hydrogen bond is very, very strong. Water is a highly stable molecule. Have you ever seen hydrogen coming out when water is heated? It is highly unlikely. When you heat water, do you get hydrogen or oxygen? Never. Even at a very high temperature also, water doesn't decompose easily. Reducing ability of hydrates of nonmetals, second point. Third point, it is their basicity. Basicity HF, HCl, HBr, HI, they are in fact acids. So, for seventh group, the question of basicity doesn't arise. For sixth group also H2O, H2S, they are not much of acids. Okay, the question of acidity doesn't arise even there. Okay, mostly fifth group hydrates NH3, PH3, NH3, PH3, ASH3, they are bases. And which is most basic? Ammonia is most basic. Why? The lone pair is free for donation. Ammonia is a Lewis base. Phosphine is again a Lewis base. But who donates more? The need for donation is more in nitrogen, because nitrogen being a small atom, the lone pair bond pair repulsions are high. In phosphorus, the need to donate is not that high. Therefore, ammonia donates a lone pair to a proton, and one who donates is called a base. B2A, this is Lewis theory in short. How come? Base is a substance which donates a pair of electrons to acid. B2A. B stands for base, A stands for acid. Base is a substance which donates a pair of electrons to acid. This is Lewis theory. So, ammonia is donating to H plus. And you know, small atoms form stronger bonds. The proton bond between nitrogen and proton is very strong. Therefore, ammonium ion is very stable, more stable than phosphonium ion. Therefore, ammonia is a better donor. And there are so many explanations. Nitrogen is being a small atom, the lone pair is distributed, the lone pair charge density is more on nitrogen. That is one explanation. Charge density on nitrogen is more. Phosphorus being a bigger atom, the charge is less densely populated. You can't see much charge here. But there is a very, very, very other good explanation that the lone pair in nitrogen is present in a directional sp3 hybrid orbital, whereas the lone pair in phosphorus is present in a non-directional s orbital. I want to explain that again. The lone pair on nitrogen is present in a directional sp3 hybrid orbital. Means ammonia undergoes sp3 hybridization, nitrogen undergoes sp3 hybridization, and the lone pair is present in a directional sp3. Means nitrogen is offering lone pair like this, take this. Whereas phosphorus, the lone pair is present in a non-directional s orbital, which means phosphorus in phosphine, pure orbitals participate, and s orbital being spherical, the lone pair is moving like this. So, phosphorus is not offering lone pair like this. Nitrogen is offering the lone pair like this in front of you. Nitrogen is offering lone pair like this, whereas phosphorus is the lone pair is present in what? Non-directional s orbital. Therefore, ammonia is more basic than phosphine. And now the question of substituted ammonia, methylamine. The lone pair encouraged by methyl group, which is called plus I effect. Methylamine is more basic than ammonia, because here nitrogen is donating, and methyl group is encouraging to donate more, donate. So dimethylamine by the same yardstick is expected to be more basic. Yes, this is a primary amine, this is a secondary amine. So tertiary amines where 3 methyl groups are there is expected to be most basic, but because of a congestion, there are 3 methyl groups, and the lone pair proton cannot approach, that is called steric hindrance. Because of steric hindrance, tertiary amines are less basic than, because of steric hindrance, secondary amines are more basic than primary, more basic than tertiary, more basic than ammonia. Okay, I don't want to go into the discussion of in what state this happens, whether it happens in aqueous state or gaseous state. That is purely related to organic. As far as I am trying to lead you to a different context, that's why I have taken up this up. Secondary amine, actually tertiary amines where 3 CH3 groups are there, they are supposed to be most basic. They are not, because of steric factors, traffic jam. There are so many groups, the proton cannot approach nitrogen easily. Therefore, though there are 3 people encouraging here, proton cannot approach because of lack of space around nitrogen. So, secondary amines are more basic than primary, more tertiary. The concept I want to discuss now is what happens in phosphorus. pH 3, methyl phosphine, a primary phosphine, CH3 secondary, tertiary. Here we expect the same order to be there, CH3 thrice P. I am talking about this. There is expected to be some kind of traffic jam, but I am telling you the steric factors don't play any role in big atoms. Nitrogen is a small atom. The methyl groups cause some kind of congestion for proton to approach. So, these steric factors are not there for substituted phosphines. Tertiary substituted phosphine. So, what is the order? Among substituted phosphines, tertiary more basic than secondary, more basic than primary, more basic than pH 3. pH 3 phosphorus is donating, CH3 pH 2 methyl group is encouraging, 2 methyl groups are encouraging, and here 3 methyl groups are encouraging. Therefore, this is most basic among substituted phosphines. Tertiary substituted phosphines are more basic than secondary. But what about amines? Tertiary, though the nitrogen is encouraged by 3 methyl groups, because of steric hindrance, tertiary occupied the 3rd place. So, what is that I am trying to tell you? The steric hindrance factors do not apply for large atoms. They are the worries faced by small atoms only. So, with that we can conclude basicity. Let us look at some of questions. First question. Have you got the question on your screen? The following are some statements related to 5A group hydrates. The following are some statements related to 5A group hydrates. Reducing property increases from NH3 to BiH3. Do we agree? NH3 to BiH3, what is happening? We have already discussed. What is happening from NH3 to BiH3? Small atoms form stronger bonds. BiH3 bond is very weak, and BiH3 has a doubtful existence. We don't even know whether bismuthine exists or not. It has a transient existence. Means, strictly speaking, BiH3, whether it exists or not also, it cannot be identified easily. So, BiH3 on heating easily gives, therefore, reducing property increases from NH to BiH3. The statement 1 is right. Look at the second statement. Tendency to donate lone pair decreases from NH3 to BiH3. Tendency to donate NH3 to BiH3. What is given there? Decreases. Yes, it very well decreases. Why? You should understand chemistry in a different light. Small atoms face the worries of lone pairs. The lone pair bothers the bond pairs. But in a large atom like bismuth, the lone pair doesn't bother much. The lone pair doesn't bother the bond pairs. Therefore, BiH3 there is no need for donation, whereas NH3 needs to donate. Therefore, NH3 is a strong base, and from NH3 to BiH3 basicity decreases. Statement 2 is right. Wait a minute. I want to warn you against something. In the last class, if you remember well, I have given plus minus minus plus. I don't know whether you remember that or not. Plus means electropositive, more electropositive, and oxides are more basic. Oxides are more basic. So what should happen? Top to bottom, basicity should increase. Okay. NH3, PH3, NH3, PH3, ASH3, arsine, stibine, bismuthine. Top to bottom, what is happening? Electropositivity is increasing. Yes, we agree. Nitrogen is a non-metal, bismuth is a metal. So top to bottom, electropositivity, metallic character, all are increasing. What about basicity? If you mistake my words, I was talking about oxides are more basic. These are hydrates. So if you mistake that basicity, if you simply say basicity increases, you should not forget whose basicity we are talking about. Whose basicity? This is the basicity of oxides. So if it is N2O5, P2O5, etc., Bi2O5, yes, we can very much say top to bottom basicity of oxides increase. Let you be warned. It is the statement is for oxides. Don't use the rule of oxides in hydrates. These are hydrates. They have a different rule. They are Lewis bases. They donate. So basicity of oxides increase. So top basicity of oxides increase, whereas basicity of hydrates decrease, because with increase in size, the need for donation decreases. Bismuth says, I need not put my lone pair under control because they are not disturbing my bond pairs. Because of the disturbance caused from this lone pair and bond pair, because of this disturbance repulsion in molecules like nitrogen, small atoms, there is a lot of disturbance because it is small. The lone pair, bond pair repulsions are very high. Therefore, there is a need for donation in the case of nitrogen, whereas there is not much need in the case of bismuth. So second statement is right because tendency to donate lone pair decreases from NH3 to BH3. Third statement, thermal stability of hydrates decreases. Yes, NH is a small atom, stronger bond, therefore thermal stability decreases. Fourth statement, bond angles of hydrates decrease from NH3 to BH3. That is also correct. How come? And we already discussed NH3, sp3 hybrid orbitals participate. sp3 hybrid orbitals participate. The expected bond angle is 109.5. Expected. Because it is sp3, everybody expects a tetrahedral angle 109.5. Once again, the expected bond angle, but the actual bond angle is 107. Why? Because of lone pair bond pair repulsion, hydrogens come a little closer, therefore bond angle has decreased. So, but in NH3 it is sp3 hybridization. I told you PH3, ASH3, etc., pure orbitals participate. Pure orbital means pure p orbitals. Pure p orbitals participate in bonding. And what is the angle between p orbitals? 90. Therefore, from NH3 to BH3, bond angles decrease. I think in phosphine it is roughly 91, or cyan it is 90, 89. I don't remember the exact values, so it's not necessary. It is enough if you know only the trend. What is the essential difference? NH3 sp3 hybrid orbitals participate and bond angle is 107. In PH3, pure orbitals participate, means there is no hybridization. If you want, in our syllabus we have only 2 molecules without hybridization, H2S and its followers, PH3 and the remaining are science T by the other hydrates. All these molecules only pure orbitals participate, no hybrid orbitals. So, first question, the answer is a very, very, very good question. It nearly covered 4 concepts. That is why I did not take up the question before I explained that. So, 1, 2, 3, 4, all 4 are right. Answer A. Answer is A. Let us go to the second question. When bauxite powder is mixed with coke, what is bauxite? Al2O3. Coke, C, is mixed with coke and reacted with nitrogen, okay, at 2075 Kelvin, look at the temperature, 18, almost 1800 degrees centigrade. Carbon monoxide and X are formed, carbon monoxide CO. Since CO is formed and at that high temperature of 2075 Kelvin, very high temperature, aluminum reacts with nitrogen forming aluminum nitride. Therefore, this X is aluminum nitride, and this is, you know, Serpex process. Serpex process in which we try to eliminate silicon dioxide. Actually, silica vaporizes at that high temperature. Silica is impurity, silicon dioxide is impurity. So, X, and when X is reacted with water, aluminum nitride reacted with water. So, what are the products? Al2O3, C, N2, you get aluminum nitride. Aluminum nitride plus water. What do you mean by aluminum nitride plus water? Hydrolysis. In the previous class, we discussed hydrolysis. Break the bond, 3H, 3OH. What do you get? Ammonia. We even mentioned that ammonia is said to be the byproduct in Serpex process. The answer is A. A, ammonia. Third question. The catenation tendency of carbon, silicon, germanium. So, carbon, silicon, germanium. What do you mean by catenating tendency? Forming long chain silicons, forming long chain germaniums, etc. Right? Small atoms form stronger bond. See how simple the answer to this question is. So, carbon will have very high energy, is in the order germanium less than silicon less than carbon. The bond energies. So, the question clearly says that germanium has less tendency. Why does it have less tendency? Bonds are weak. They can't be, you can't make a garland with very heavy objects. Maybe you can make a garland of small grapes, garland of grapes with a thread, But can you ever make a garland of coconuts with the same thread? Heavy. The bond, that catenating tendency is not there. And what about bond energies? Small atoms form stronger bonds. Therefore, CC, there are 3 values given, 167, let us write the 167, 180, 348, 180, 348. Therefore, this is weakest bond, germanium. Second weakest, silicon, carbon. So, carbon bond energy 348 kilojoules per mole. Let us go to the next question. Answer must be carbon, silicon means answer must be D. 348, 180, 167. Answer is D. Fourth question. Once again the same question. pH, ASH, NH, small atoms form stronger bonds. So that is why I took all the trouble in explaining thermal stability. You must know these are all previous questions given or already given questions. pH, ASH, NH, small atoms form stronger bonds. So, NH bond is the strongest. 389 will go to NH. So, wherever 389 is highest, that is NH. Second highest is pH. Third highest, you just make a 247. What are the other values? 389, 318. So, this is NH bond, pH bond, ASH bond. You look for the option wherever it is. The order asked is pH, ASH, NH. So, 389 must be at the end. ASH, this must be in the middle. So, pH. The question starts with pH. Therefore, 318, 247, 389. What is that? Where do you have that? maybe in D. 318, 247, 389. Option is D. So all questions you have seen 3 questions in succession. Concept is one word or one phrase. Small atoms form stronger bonds. Everything about halogens in their elementary state is an exception. Let's go to the next question. The correct order of reducing ability. Once again, so I am bored of reading all these questions. Small atoms form stronger bonds. NH bond is very strong. Ammonia is a molecule which on heating doesn't give hydrogen easily. It is not a good reducing agent. 6th question. Which one of the following statement is correct with respect to basic character? We discussed that very much. Triphenylphosphine. Trimethylphosphine. There are no steric factors. Therefore, CH3P is more basic than PH3. Which option do you find the answer? I think it is D. PCH3 thrice. PCH3 thrice is more basic than PH3. Whereas it is not the same in the case of substituted ammonia. When nitrogen is there, nitrogen being small, methyl groups, though they encourage, they hinder the incoming proton. The lone pair is not available for donation. There is a lot of food in a place, but there is no room for eaters. Room is full of caterers. There is a lot of food is there, but those who are coming to enter, there is no place for them to eat. Next question, please. Which one of the following cutter for bond energy? Okay, don't fall into the same trap. What is that? Small atoms form stronger bonds, but everything about halogens is an exception. What is it I told you? Expected order is fluorine greater than Cl greater than Br greater than II. So fluorine is expected to the winner. Fluorine is expected to be at number 1 position, but fluorine goes to 3rd position. I will add a little here. Just listen. Bond energy. We expected bond energy of fluorine to be very high, but fluorine took the 3rd place. Cl, Br, F, II. The last one is II. So here it is. I expected fluorine to be the winner, but he got the 3rd place. Electron affinity also in general is more for small atoms. So once again I expect fluorine to be the winner. He disappoints me once again. I expected him to get the 1st rank. He got 3rd rank. And again I expect him to get the 1st rank, but this time he gets the 2nd rank. Chlorine, fluorine, bromine, iodine. You see how small atom, fluorine is small atom, so I expected FF bond to be very strong, but unfortunately fluorine won the 3rd place. 2nd place here. So it's like a person who could not win a quarter-final match. Quarter-finals he lost. Next time he lost in the semi-finals. I thought, how can he win the cup? But fluorine wins when it matters. Quarter-final, semi-final, they are not important. Fluorine wins the World Cup. That is, fluorine no doubt disappointed. In, what is that? A small Asia Cup. This is a Champions Trophy. Fluorine, quarter-finals, defeated in Asia Cup, but defeated in semi-finals in Champions Trophy. But fluorine brought the World Cup. What is World Cup for non-metals? Non-metals are supposed to be champions when it comes to oxidizing ability, and oxidizing ability of fluorine is more. So what is important? World Cup, and fluorine wins the World Cup. So why was I disappointed? It's a small match. It's a small cup, Asia Cup. You lost in quarterfinals. A Champions Trophy over only 6 nations are playing, and you lost in the semi-final. How can I expect you to win the World Cup? Fluorine wins when it matters most prestigious. Non-metals, what do you expect a non-metal to be? A powerful oxidizing agent. And And the real test for non-metals is their oxidizing ability, and fluorine wins when it matters most. The smaller titles, okay, but well, that is it. Why? Why? In general, somebody has strong affinity for electron. Electron affinity means the affinity to win, the match. So, chlorine hasn't got that affinity, but still won because of its greater hydration energy. Okay. Now, the question is simply about bond energies, but it is not enough if you just answer this question and applaud yourself, very good, I did well. No, it is not just enough if you answer one question or two. You should answer all questions relating. No doubt the question is about bond energy, but when we are talking about bond energy, you should talk about what happens to electron affinity, what is their oxidizing ability. So, like this. Next question, please. Bond dissociation energies of HF, HCl, HB are same thing. Small atoms form stronger bonds. Next question. The oxidation of iodine in, that is not IC, there is a printing mistake, that is ICl2 minus. ICl2 minus, you correct in your notebook perhaps, ICl2 minus. So, you have 2 chlorines minus 2, iodine is plus 1. The oxidation state of iodine is plus 1 in that molecule. Next question, please. The gas that is used for sterilizing water, it is a revision question. As usual, last 1 or 2 questions I am using. So, sulfur, NO2, O3. What is the fourth option? It is NH3. NH3. Please, which can be used for sterilizing water. What do you mean by sterilizing water? Sterilizing means killing bacteria. I told you in the last class, bacteria dies of oxygen. Bacteria, we live of oxygen, we live with oxygen, but bacteria dies of oxygen. And which of the following gives oxygen very easily? Ozone. Why? You know, ozone, there is an oxygen single bond. There is an oxygen single bond with too many lone pairs. Same once again when it comes to bond energies. Okay, small atoms form stronger bonds. Therefore, with too many lone pairs in too little space, the bond breaks easily. Ozone easily gives oxygen, which is nothing but which kills bacteria. So, these molecules H2O2 in which there is a weak oxygen bond is there, CaCl, OCl, HOCl, 2 lone pairs, 3 lone pairs, 2 lone pairs on oxygen, 3 lone pairs on chlorine, O3, O double bond O, single bond O, dative bond of course. So, all these molecules, the bonds are very weak, oxygen atom comes out easily, therefore, all of them can be used wherever you need an oxygen, sterilizers, water purifiers, bleaching agents, what not, they can be used for many purposes. Okay, let us go to the next concept in the form of a question. We just look at, this will be the last question, this will be the, which one of the following has highest boiling point? Helium, neon, argon, krypton. What is the question about? Don't look at the question anymore. Highest boiling point. Now, we will look at a concept using which we can answer thousands of questions. Not just one, thousands, hundreds of questions. What do you mean by boiling? Suppose you take helium in liquid state. Right? Liquid state means atoms are very close. Helium in liquid state. You have to convert that to helium in gaseous state. So, helium atoms are there. They don't touch each other. Don't mistake me. They don't touch each other. Even in liquid state, they don't touch. They maintain some respectable distance even in liquid. This is liquid state, right? So, this is liquid, and so what do you mean by boiling? Separating atoms, molecules, ions as far as possible. So, to separate these two atoms, what is it you should do? You should remove whatever attraction exists here. Whatever attraction exists. So, intermolecular forces. You have to overcome interatomic, interionic, intermolecular, in general interspecies. This is a species. Interspecies attractive forces. So, you should avoid. So, boiling point, it is not just boiling point, you will be surprised, I will give you a host of things. Boiling point, critical temperature, ease of liquefaction, how easily you can liquefy a substance, ease of adsorption, okay. So many things like this, all of them are directly proportional to intermolecular forces of attraction. Intermolecular, I would want to say interspecies, intermolecular force of attraction. There can be one or two exceptions, but 99% of cases they depend on intermolecular forces only. Listen, boiling point, critical temperature, so what is liquefaction? Bringing molecules in gaseous state together. What do you mean by liquefaction? Bringing molecules in gaseous state together. When will the molecules come together? When there is a force of attraction. If 10 people want to gather at a place, there should be some friendship between them. If only they are friends, they gather at a place. Otherwise, why 10 people will collect at any place? Similarly, what is adsorption? Molecules getting attracted by a surface, air molecules getting attracted by the surface and sticking to the surface. They should stick to the surface like this. They should not come out. So, if the molecules want to stick to the surface, there must be some intermolecular force between them. So, greater the intermolecular force, greater will be the boiling point. And how many types of intermolecular forces are there? How many types of intermolecular forces are there? Excuse me for this word, molecular, actually I mean species. Intermolecular attractive force. Intermolecular attractive force are four varieties. Metallic attractions which exists in metals. Metallic attractions. In general, metallic bond is stronger. Bonds in metals are stronger. There can be exceptions. The metallic bond in some substances may be weaker also. Very highly polar substances. Very highly polar substances which you call as ionic substances. So attractions between metals, metallic attractions, very highly polar. The third one is highly polar. Highly polar you will see only in hydrogen bond, and hydrogen bond is there only when FH, OH and H bonds are there. I repeat, FH, OH and H bonds are present. Only. There are one or two cases where chlorine also participates in hydrogen bond, but don't spoil your brain with that knowledge. That knowledge is not necessary, especially at this time. So, FH, OH and H only. Highly polar means hydrogen bond. And if these three are not there, I repeat, if the given set of substances are not metals, they are not ionic substances, they don't contain highly polar, all other categories they are called less polar or non-polar. All other categories are called less polar or non-polar. And less polar, non-polar, the force of attraction is called van der Waals force of attraction. It is similar to gravitation. Don't mistake me. I never said it is gravitation. It is similar to gravitation, means it depends on whatever factors gravitational mass. So, the van der Waals force of attraction is directly proportional to atomic weight or molecular weight. Atomic weight or molecular weight. So, first of all, you should rule out the possibility of somebody being a metal, ionic, highly polar, Then you talk about mass. When should you talk about mass? Only in the absence of these three. So, let us look at a set of substances. So, in fact, the heading to this particular topic, it is not just hydrates we are going to discuss. We are going to discuss all substances we know, all substances in our syllabus, the boiling point of all substances, the way we can, whether we can liquefy them or not. So, the heading is actually intermolecular forces, intermolecular force of attraction, intermolecular forces. Of course, we discuss the boiling points of hydrates also. We are not sticking ourselves to hydrates. So, what is it I am trying to tell you? Don't learn a particular question. You see where else the same logic applies. In thousands of sets, 1. Helium, neon, argon, krypton, xenon, boiling point, right? Boiling point. Helium, neon, argon, krypton, xenon. Are they metals? If they are metals, I will talk about metallic bond. They are not metals. Are they ionic substances? No. If they are ionic substances, I will be talking about their lattice energies. I would be talking about lattice energies. They are not ionic substances. How do you know? They are not even compounds. They are elements. And for an ionic substance, metal is a must. For an ionic substance, metal is a must. I am not telling you if there is a metal, it is an ionic substance. No guarantee. If there is a metal, it is an ionic substance. But for an ionic substance, for example, CrO2, Cl2, chromyl chloride, you have a metal here, but that is not an ionic compound. That is a perfectly fairly covalent compound. Double bond O, Cl, Cl, right? CrO2, Cl2, chromyl chloride. You have a metal. So, I am not guaranteeing that if metal is present, then it is ionic. No. But for ionic substances, metal is a must. So, no metal, therefore not ionic. They are not even compounds for that matter. Do you have hydrogen bond? For hydrogen bond, you need to have a bond. There is no bond at all. Helium, we are talking about atoms. So, what governs helium, neon, argon, krypton, xenon, or helium, neon, argon, krypton, just take 4 of them. The boiling point now depends on mass only. When is it I am talking about mass? When they are not metals, when they are not ionic substances, when they are not ionic substances, when you don't have hydrogen bond, in the absence of these three are not there, then just blindly go by mass. So, you have helium less than neon less than argon less than krypton. So, this is question number 1. Boiling points of helium. Krypton, why is it more mass? Van der Waals force is more. So, the force of attraction, what exists between two helium atoms? What exists between two helium atoms? I will jokingly say nothing exists. What exists between two helium atoms? Nothing. That next to nothing is called Van der Waals. Van der Waals is a very, very, very negligible, weak force of attraction. But why am I talking about that negligible? There is nothing else to talk about. To compare helium and krypton, what is there? What is there between two heliums and two krypton? Nothing. So, that next to nothing Van der Waals depends on mass. Therefore, between krypton atoms, because of their heaviness, don't think that they are too heavy. They are heavier only than helium, neon, argon. Because of their heaviness, there is some kind of a little more intermolecular force. So, the boiling point of krypton is higher than that of helium. So, in fact, I have prepared some 24 questions, but the heading to all the questions is the same. Therefore, I don't want to show you the questions, I just write like helium, neon, argon, krypton. Second set, methane, silane, germane, stannane. Methane, silane, germane, stannane. Germane, stannane. Please tell me, are they metals? Same order. Are they metals? You ask yourself, are they metals? Are they ionic? Are they hydrogen bonded? If nothing, Van der Waals. Van der Waals means mass. Are they metals? No. Ionic? No. I am talking about these 4. I am talking about methane, silane, germane, stannane. Are they metals? No. Are they ionic substances? No. Are they hydrogen bonded? No. Because hydrogen bond will be there only when fluorine, oxygen, nitrogen is there. Don't remind me of substances in which chlorine also participates in hydrogen bond. That is not necessary at this point. So, So now only mass, methane has less mass, therefore the boiling point of stannane is more. 3. HCl, HBr, HI. HCl, HBr, HI. Boiling point of these 3. HCl, HBr, HI. Once again, are they metals? Are they ionic? There is no metal. For somebody to be ionic, the presence of a metal is a must, right? So once again, do you have hydrogen bond? No, hydrogen bond is there only when fluorine, oxygen, nitrogen are there. And hydrogen is attached to them. FH bond, FH bond, OH bond, NH bond. These 3 are a must for hydrogen bond. Now, only mass, okay, there is nothing else to compare. Only mass is the tiebreaker. Molecular weight of HI is more. 4th one, H of HCl, HBr, HI. I have consciously removed HF from this. I have not given HF in this particular. So, if you carelessly, if you are a little careless, or if you consider only mass, what will you do? HF less than, HCl less than, HBr. And when I ask you, why are you talking about mass? Sir, there is nothing else to talk about. No, there is something else to talk about. HF has hydrogen bond. So, the boiling point of HF is the highest, though it has less mass because of hydrogen bond. In HF, there is a special attractive force, HF, hydrogen fluoride, HF, intermolecular force is hydrogen bond. Okay? So, be careful. Don't use mass. Mass is not always the mantra. Sometimes you may have to look at a different molecular force also. Similarly, H2O, H2S, H2SE, H2T, H2T. You may think water has less mass, but wrong. So, you write the wrong order, you wrong it and put it the right place and give the reason for the anomaly. H2O, hydrogen bond. So, which of the following can be liquefied easily? Same question. Water. You need not liquefy water, it is a liquid at room temperature. Does H2S exist as a liquid at room temperature? H2S is a gas. Why? There are no intermolecular attractions. If molecules have attractions, they come together. If they come together, somebody becomes a liquid. So, ease of liquefaction, ease of adsorption, critical temperature, all of them depend on intermolecular force of attraction and mostly van der Waal. Now, so you study ease of adsorption in a topic called surface chemistry. You study critical temperatures, ease of liquefaction in a topic called gaseous state. Boiling points we generally study in chemical bonding as well as groups. So, so many chapters, same concept. So, you have to interrelate concepts and study, never make any what you call isolated study. Don't learn like a watertight compartments. There is interrelation between every 2 questions. You observe what is the binding thing. Now, NH3, PH3, ASH3, SbH3. What is your expectation? As usual, you expect NH3, okay, mass. This is the expected order. But NH3, there is hydrogen bond. Therefore, because of hydrogen bond, intermolecular force of attraction, because of hydrogen bonding, NH3 surpasses, overtakes PH3, ASH3, but perhaps it cannot surpass SbH3. Therefore, NH3 comes only 3rd. Listen to me. In other cases, HF topped his list, H2O topped his group, but NH3 only 2nd. No doubt, ammonia, there is something called intermolecular hydrogen bond, but the van der Waal force of attraction SbH3 itself is more than the hydrogen bond attraction in NH3. So, in all others, hydrogen bond is the topper of the list, but even though hydrogen bond is there, okay, just to remember that with ammonia there is some difficulty. So, like this you can answer any number of questions. Think of it, Which of the following can be liquefied easily? H2, CO2, NH3, NH3 and N2. Which of the following can be liquefied easily? What will be the answer? Whichever has high intermolecular force of attraction. Which has high intermolecular force of attraction? Ammonia due to hydrogen bond. Ammonia can be liquefied easily, can be compressed easily. That is why it is used in compressors of refrigerators. Because it can be compressed easily. To compress ammonia gas, you don't need a lot of force. It easily compresses. So the moment the gas is compressed, the gas takes heat from the refrigerator and expands, and the electric motor once again compresses it. So it is an easily compressible gas. You can't compress hydrogen because you can't bring hydrogen molecules together easily because they don't want to come together. That is the question. They don't want to come together. Okay. So like this you can answer any number of questions. And methane, just lost 2 minutes. Methane, ethane, C2H6, C3H8 propane, C4H10 butane. Yes, what is the conclusion? Think about mass. Why am I talking about mass? Why am I talking about molecular weight? They are not metals, they are not ionic, they are not hydrogen bonded. Therefore, there is nothing else to talk about. Therefore, we are considering only butane. Last question. N-pentane, isopentane, neopentane. Another question. Fluorine, chlorine, bromine, iodine. Boiling point of which is more? Fluorine and chlorine are gases at room temperature. Bromine is a liquid. Iodine is a solid. What does it tell you? As the mass increases, the intermolecular forces are increasing. Therefore, they are coming together. Fluorine molecules far apart. Chlorine little apart. Bromine very close. Iodine is a solid in fact. Intermolecular forces are increasing. So even first 5 alkanes are gases. Next 10 to 12 alkanes are liquids. Higher alkanes are liquids. Why are they liquids? Because the molecules come close. Why do the molecules come close? Because there is a lot of attractive force. Why do they have a lot of attractive force? Once again, mass, their mass is more. And what about these three? Last question. N-pentane, isopentane, neopentane, right? They have same mass, they are isomers. So among isomers, more branches, less van der Waal. So in neopentane you have so many branches, neopentane. Isopentane there is one branch, isopentane one branch, neopentane two branches. So more branches, less van der Waal force of attraction. Therefore N-pentane has it. Why am I talking about branching? Because there is nothing else to talk about. They are not metals, they are not ionic substances, they are not hydrogen bonded. And if I want to talk about van der Waal, their mass is also equal. Since there is nothing else to talk about, we are talking about. Okay, with this we can finish. You can answer any number of questions like this. Okay, thank you.